So this is a Mosfet example. So this is falls into the category of transistors. And once again, whenever you are given a transistor problem, first thing is to figure out what kind of transistor you're dealing with. Obviously here it was mentioned in the problem, but just in case it's not, just double check in your handbook to do configuration comparison real quick. So this is a symbol that we have here, so you know that you're dealing with a MOSFET. And even not, we also have the relationship. There's kind of exactly how it's written here in the problem. Okay, so now we know that we're dealing with MOSFETs. And so second thing is to put out your drain, your gate, and your source in your problem if it's not given there. Okay, so here is my drain, and this is the gate, and this is the source. So now we can read the problem. Well, reading the problem is actually the first thing to do, but so the problem gives you two regions, where if it operates there, you have a particular formula. So if it operates in the triad region, then you have ID is equal to this. If it operates in the saturation region, your ID is this. Now, they tell you in the problem. So this is the clue. That's the only clue you have here. So because you don't know, what region it's operating, you can't really proceed unless you know. And that's typically with a MOSFET problem. So it either operates in a triad, in a cutoff region, or saturation region. So you have to figure out which one. And they typically tell you that. I mean, not tell you, but they typically give you a clue in the problem, and a hint in the problem, kind of that would lead you to knowing exactly which region you're dealing with. And so here, this is a particular hint. I was just saying clue, but yeah, this is a hint. So the hint says that the FE operates in saturation region for VDS greater than is greater than that. So if we know this thing, if we verify this relationship to be true, then we know we're operating here. If it's not, then we're operating here. So now the second thing would have been to actually that's what I do typically in a transistor problem, is to put out my voltages. I forgot to do that. But your 5 volt is your VGS. That's that's the voltage going from G to S, your gate to the source. We can put that there. From here to here, that's your VGS. That's your 5 volt. That's 5. It's always a good idea to understand what goes where. And your 15 volt is actually the voltage across the whole entire circuit. That's the source voltage. So don't mistake that with thinking, because a lot of our students will think that the 15 volt is the voltage across the resistor, and it's not. It's actually the voltage across the entire circuit. So it's also a good idea, just like I did in the BJTs, to put that this entire thing is your 15 volt. That's your VS, if you will. So that's my voltage, source voltage, and so we can put that there as in 15. And this is already given. That's your VDS. That's your voltage from your drain to the source is already given as 2 volt here. So we can add an S here if you want. You weren't told that in the problem, but we know that. Okay, so this is always a good idea to do that. Now we can proceed. Now that we've done the basics, so always start with the configuration. Put out your drain, your gate, your source. Put out your voltages or your currents, and then proceed to solve the problem. After, of course, understanding what they're asking you. So here we have VDS. Greater than VGS minus VT. Yeah, it's small d. Do we know? We don't know. So what's VDS? It's given as 2. So now we don't know if it's greater or not. VGS is 5. VT was given as 1. Minus 1. So we have 2 here is less than 4. So this relationship is not true. Therefore, it's not operating in the saturation region. It's therefore operating in the triad region. So we're only dealing with that particular formula in this entire problem. So we can erase this so we have space here. Now we can calculate ID, because we're going to need ID in order to figure out what R is. Okay. Where's my pen? Okay. So ID is K, would be 0.5. In this case, where I have a lot of different values, I typically put the units just so I don't get things mixed up. So I have V squared here. Okay, this is A. And I have 2 here. VGS minus VT, we already know that's 4, because that's 5 minus 1, so we can put a 4 here. VDS is 2, and we have 2 squared, which would be 4, and that's it. So this was squared, so we have voltage squared. That would have cancelled out with this, so we know that our result would be in milliamp. That was the purpose of putting the unit here. Okay, so we have 2 times 4 is 8, 16 minus 4 is 12, so we have 12 times 0.5. I'm still using a calculator. So we have wait, I have 6 milliamp. I'm sorry. So that's my ID. Okay, so what do we do from here? We know what ID is, and we have the voltage. We will find out the voltage across the R using Ohm's law. So from here, we can say that R, what's R, using voltage, R, V is equal to IR, so R will be equal to V over I. So what's my voltage though? The voltage across the resistor, which would be what? If you look closely, this is the voltage that I need across the resistor. Then obviously, if I know this voltage, which was already given as 2 volt, which is the VDS, so if I have this minus this, that will give me the voltage across the resistor. So that's why it's always a good idea to put it that way. So we have 15 minus 2 over 6 milli. So I have 13, no, this is milli, over 6 milli. So that's 13 over 6. It's 2.16. So that will be, the answer will be in K, because 10 to the power 3. So my R, final answer, let me put that in white color. R is therefore 2.16 kilo ohms, and that's it. Pretty straightforward. So just to kind of recap, Mosfets or Jfets, typically it's operating in either region sometimes, so they will give you a clue or hint or something to kind of tell you which region is operating. Sometimes they will actually ask you, in what region is a MOSFET operating from? So somewhere in the problem is going to be given. So you just go off of the actual assumptions here. So either you calculate this or you calculate that to figure out. But in this particular problem, this was given. So if we figure that out, then we go from there. So once we find out what region it's operating, then it's pretty much easy. And so the point to take care of is also to always remind yourself to put the voltage. That's always a good idea to do that, because sometimes I've seen it happen in my classmates. They think that the 15 is the voltage across here, so they would have easily, instead of 15 minus 2, they would easily put 15 over 6. And so I'm sure in the problem 15 over 6 would give you something, and that's true, because in the multiple choice questions there is actually a 2.5 there. So if you solve the problem wrong, there's an answer down there that's also wrong, but you would think you get it right because you already solved the problem. So you have to be extremely careful. So in the choices down, what I'm looking at, because I have the this is from the NCES, there's a multiple choice question says 2.5 and 2.17. So if you put 15 over 6 here, you will have 2.5, and so you will check that as your answer, thinking that is the correct one, but it's not. So always that's how they trick you out. So if you solve the problem wrong, there's an answer down there. So you have to be really, really careful with that. So with transistor problem, it's always a good idea. Always start with putting out your gates, your drain, your source. If it's BJTs, you put your emitters, your blah blah blah, and then put out your voltage like this, to kind of see it. I think I've answered most questions that you would typically ask, but yeah, if you have any questions, you can write me an email or put it down on the comment section. Alright, thank you.